Hey there, I'm Yakov. This is the Swiftbird, a channel about software and tech. In this series of videos, I cover the key concepts of Swift, iOS app development, and everything in between. My idea is to create some sort of a guide which you, as well as the future I, can use as a refresher whenever needed. Before an interview, for example. I broke it down into domains such as memory management, threading, and user interface. And I present each domain as a series of questions, something similar to what you can get in an interview. You see, in my career as a software engineer, I've taken dozens of interviews for myself and probably interviewed at least 100 candidates on behalf of my employers. Because I'm just getting started with this series, your feedback is very important. Don't hesitate to leave a comment about what you like and what you want me to change. And as always, I'd really appreciate your thumbs up and subscription. You will also find the links where you can support this channel below this video. Thanks, and now let's begin with the most essential questions about memory management. You might notice I didn't even say memory management in Swift. That's because these most essential questions are more or less the same for any programming language. And the most essential question of all is what is computer memory and why the computer needs it in the first place? The answer is pretty obvious to anyone who's somewhat familiar with a computer. But interviewers, myself included, sometimes ask obvious questions to see how much of a big picture the candidate can see. Feel free to skip the section if you can give an answer all by yourself. And for everyone else, I'll try to give an answer that's neither too simple nor too complex. Well, random access memory is the primary kind of memory the computer uses to store data and processor instructions. This also includes your program, because its compiled code is stored in the RAM as well. It's called random access because any region can be accessed at constant time, without the need to move the head or rewind the tape. Yeah, magnetic tapes are still a thing, mainly for long-term storage. So basically, everything you write as a software developer ends up in the RAM, from where it can be retrieved in almost no time. That is the big advantage of RAM over other storage media, such as SSDs. It provides much higher access speed, called bandwidth. Today it's often somewhere in the hundreds of gigabytes per second, while the fastest SSDs only give you 10, maybe 15 gigabytes. And hard drives are kept at under a single gigabyte. That means your program can react to any user actions almost immediately, without the user noticing any delay. That's in contrast to other storage media. For example, I use an external SSD to edit the Swiftbird videos, and a large hard drive to store the original footage. Whenever I open the library, it takes my computer a second or two to read the project, load it into the RAM, and display in the timeline, plus a few more seconds to find every original clip on the hard drive. While that's being done, all I'm seeing is either a loading bar or placeholder images. Imagine how many more videos I could make if everything was stored directly in the RAM. Unfortunately, it's not possible, and that is the main disadvantage of RAM. Because of the speed and other technical challenges, every gigabyte of RAM comes at a higher cost than the same gigabyte on an SSD. Besides, there's only so much data you can process in any given time, so storing everything in the blazing fast RAM is not really efficient. Another feature of RAM is that it's volatile. That means RAM modules need constant supply of power, otherwise they lose all the information. So when your app is doing something long and important, it's best to save any intermediate results on the disk. So that is computer memory. But why do we need to care about its management? That's coming up next. Even if you skip the previous question, you probably know that the amount of RAM is limited. Your computer can have terabytes of SSD storage, but only 16 gigs of RAM, or even 8. Apple apparently thinks 8 gigs is enough for most people. That's why it puts 8 gigabytes in its most popular Macs. And when you want more RAM, you know it can get expensive. And I'm not even talking about Apple's bizarre pricing. Well, I think you get the idea. As a developer, you want to make your app accessible to as many people as possible, so you can't assume that the user has an unlimited amount of RAM. That is why you need to be conscious of how you use it, and make sure you do it efficiently. But even when you do your best to not waste any bytes, you can still end up accidentally taking more memory than intended. That's because without applying some management techniques, it's very easy to make a mistake, whose consequences can range from memory leaks to random hangs and crashes, to your app becoming an open door for viruses and other malicious stuff. I'll talk about the mistakes in memory management later in this video. Finally, even though the modern day's RAM is blazing fast, it still has its limits. So even on the latest and greatest hardware, you can still see the difference in performance between an app which uses the memory efficiently and the one which doesn't. Luckily, most modern languages provide the tools which make efficient memory management an easy task. Swift is not an exception. I'll be having a look at Swift in the next episode. But before garbage collection, reference counting, and similar things became widespread, the memory had to be managed manually. You don't often need those skills today, but knowing about the principles can still be helpful. Manual memory management is the foundation of any sort of memory manipulation. Every other approach is based upon the very same set of operations, except you don't see the explicit commands, because the compiler or runtime calls them behind the scenes. Manual memory management is a nuanced topic, which deserves a separate video. But anyway, you don't normally get many questions about it in interviews, so I'll only touch on the very basic principles of manual memory management, and mostly as a prerequisite for the next topic. In this setup, you are responsible for allocating and deallocating regions in the memory. In other words, you have to tell the computer when it needs to find some bytes for a new object and when those bytes are no longer needed. But allocating memory is not enough. You also need a way to address it, so you can read and write data. For that, you use pointers. They're just variables which hold memory addresses. And when you dereference a pointer, you get the data stored in the memory. Pointers make accessing the memory more convenient, but that's just about it. There isn't anything magical about them. So, manual memory management basically involves only three things: allocation, deallocation, and pointers. But what and when you do with them is extremely important. Any mistake will result in a bug, and memory-related bugs are the dominant cause of crashes and security problems. The problems you get when you mess up manual memory management are well known, and they have been since, the 70s. But they're still widespread regardless, because today's software heavily depends on memory-unsafe languages, such as C and C++. For example, Microsoft says memory issues are responsible for about 70% of all security problems. Take a look at this timeline. It shows the correct way of working with memory. But basically any deviation from this will result in an error. When you forget to deallocate the memory, it's called a memory leak. With time, the amount of free memory becomes smaller and smaller, until the computers run out of any unused bytes. It's as if you took a book from a library but didn't return it. At some point the library will run out of books and will not be able to accommodate any new readers. But deallocating memory just in case is not a solution either. When you do that to a region that's already been deallocated, it's called double free. In manual memory management, the computer is really dumb, but also really obedient. It does whatever you say, without thinking about any consequences. So by the second time you call free, the memory may already have been taken by another object. Your call will corrupt the contents, and you won't even know about it until later. Reading the memory at the wrong time can also lead to problems. When you deallocate memory, it's also important to get rid of the pointer. A dangling pointer is one that points to the address in the memory that's already been deallocated. And when you try to dereference the pointer, you get not what you expect. In the best case scenario, the runtime will catch this attempt and crash the program. And I repeat, this is the best case, because otherwise it will just return the data as if nothing changed. This is serious, and this is bad, because fooling the computer into reading and executing their own data is the mechanism that powers many kinds of malware. In this video, I've had a look at a few most essential questions about memory management. From the interviews I've had, either as a candidate or interviewer, I would say these kinds of questions are equally common, no matter what your level is or what kind of position you're interviewing for. In the next episode, I'll be talking about intermediate level questions, most of which are specific to Swift. That's it for today's video. You'll see the next one very soon, and if it's already out, you'll find the link here. If you found this episode helpful, please give it a like and subscribe to the channel. This will help other people discover the video. And at the links below, you can support my future work on the channel. Let me know in the comments what kind of questions you were asked when you interviewed for your first engineering job, and what you would ask a junior developer. Also, I'm always open to your feedback. See you later, and until then, make your skills fly.